So, a very good afternoon to everyone. So, I am Rohit Gehlot and I will be the TA for this theory of production processes for this semester. So, the course is a 12-week course, and I think you have already received for week 1 and week 2 uh, lectures and videos, and also you might have also received the assignment which you need to submit for the week 1. I hope everyone is able to do some submission for this. So in the week 1, these 5 lectures were floated. First one was the introduction to theory and practice of casting. Second one was the solidification cooling areas. Third one was the solidification for the pure and alloy system, I think. Yeah. And the fourth one was the factors affecting solidification, finally followed by the fluidity. And after that, I think the assignment was floated and the quiz was for your evaluation. So I hope everyone has already been through those lectures because in these videos we might be solving majorly the uh, numerical portion. So we would be solving majorly the numericals and all. So as seen like presently I think no one has joined. So I will wait for 5 more minutes and after that we will start the discussion on the numericals and the subsequent MCQs. Okay, so good afternoon to everyone. So I am Rohit Gehlot and I will be the TA for this theory of production processes courses. So this is a 12-week course and I think the 5 videos have already been uploaded for the week 1 and the major topics were covered were the introduction to theory and practice of casting, solidification and cooling areas, uh, solidification behavior of pure and for the pure and alloys, and factors affecting solidification followed by the fluidity. So majorly we will be, I think everyone has already been to those videos, and so in these tutorial like for the following 12 weeks, we will be focusing on the numerical portions. So if you or else if you want to cover any particular topics, please intimate me by dropping me a simple email. So I will be sharing my email to you, and also the in the next week I will be sharing the folders of these recorded videos as well as the PPT slides for the PPT slides covered in these lectures. So if anyone has any doubt or want to say something, he or she is free to do so, or else we will be starting the discussion. Okay then, so as it is a 12-week course, so first 4 weeks will be devoted to the casting, and and then the subsequent Sundays from 4 to 6 we will be discussing about the various numerical portions for all the 3 portions. as covered by the Professor Jha. So in each week, if you have any particular doubt, or if some particular topic is not covered, you will be already intimating me via mail previously before Sunday, so that I will be as per your needs. I will be preparing my slides according to that, or else like uh, we will be as the major focus of these tutorials are to do the to give you the exposure of different problems, so which will be helpful in the final exam of yours, as well as any of the upcoming exams, and to clear your doubts during your 7 days classes of your weekly classes shared by you. So firstly, we will be doing some MCQs, and after that we will be solving some numericals. Or else, if you want to change the trend, if you have any suggestions like what should be covered in these tutorials, because these are majorly devoted for your solving your doubts. If you have any suggestions, any one of you, you're free to discuss. I will wait for 2 to 3 minutes, and after that, we will start with the MCQs and then numericals. Okay. So Francis, have you been through all the videos shared with you? Sorry. So I'm saying have you been to all the week ones videos and all? Okay. 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 So if you have any suggestions, majorly students are preparing for GATE, that's why uh, they go to these courses. So if you have any particular need, particular numericals and all, if you want to cover on in these, because weekly 2 hours you need to spend here, so let's make it interactive and more beneficial for you. So if you have particular needs, these are the topics, these are the numericals, these are the set of numericals I got doubt while solving after watching through the lectures, then that will be more beneficial to you, as well as the session will become more interactive. It will be beneficial for me also, because as you can see, only you have joined, no other students have joined. Every year it is the same story. So if it will become more interactive, it will be beneficial for you also. Yeah. Shrinkage problems. Okay. So I have I will share my mail ID on this. So you can share those problems to me. So you can share those problem to me. So in the next tutorial, next Sunday, we will be discussing those. Or if any particular topic in which concept you are having some conceptual problem, we will discuss. We can discuss that also, which will be fitting in this courses curriculum. Okay. Okay. So so is any particular book or any particular author you are following, or on the previous or those are the previous year questions of the GATE or some other exam? Okay. 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 So so what you can do now, just make a screenshot of those questions. Okay, and also with their solutions, it that like in particular this step I got doubt, or like this particular concept, like how this equation they wrote and something like this. You can make a PDF and share to me by before Saturday of this next week. Okay, so I will be including those in this presentation, in the next week's presentation, because this is our first week, so no, so not much interaction with the students. So that's why I prepared haphazardly like these presentation. So the next week it will be better if you will share those, no? Okay, okay, okay. Then. So this I so majorly I have in this week I have added only basic questions, basic MCQs and basic numericals. So these are not much difficult. So I think you can easily solve those. So we will go them one by one. So these are basically the previous year's questions which were asked uh, for the students to solve. So so I put them in presentation, and then after that I have added some numericals also. So which I will be solving for your ease. Okay. So Francis, if you got any doubt or in these MCQs, we can discuss it, or else you can say what you think, what is the answer of this particular MCQs. Okay. So first, okay. So the first one is which of the following comes under the category of shaping of the material. So if you want to comment on this. Yeah, casting will be definitely will be there. So if anyone, okay. So okay. Okay, so what happens in the shaping of the material? So if you talk about casting, definitely it is one of the answers. So now when you are talking about annealing and powder metallurgy, so in annealing basically we do for if you go to the basic definition of annealing, so in annealing it can be in furnace or out furnace. So basically the crystal structure and the inherent properties like mechanical properties, strength, toughness, they all get changed by annealing. So, but there is no shaping of the material which gets changed by due to this. On the other hand, when we talk about the powder metallurgy, so in powder metallurgy we can mix different powders. We can synthesize them by compacting them in a particular shape, and on the other hand, we can control the properties at the microstructure level. So the correct answer will be casting and powder metallurgy. The annealing is more about controlling their uh, properties instead of shaping of the material. So the answer will be the casting and the powder metallurgy. Yeah, in powder metallurgy we can compact and make a center of that, and beside that we can in powder metallurgy have a lot of applications when we from gear making to some bigger elements also we can find the powder metallurgy applications, because we can control very minute details when you talk about the powder metallurgy. So if powder metallurgy comes in your curriculum, there is one course by IIT Madras professor is also being floated in this semester. If it comes to your curriculum, if you're in your GATE exam or something, you can also go through it, because it is a very good field to make a career in it if you go for higher studies or some other thing. Okay then. So let's move to the next problem. So like it says about which of them is not the characteristics of the casting processes. So the first one is ease in manufacturing large size product, design versatility, flexibility of process, and D is highly expensive processes. So I think it is a easy one. So definitely why, yeah. Yeah, like when we talk about casting processes, like there are different types of casting processes which Professor Zha will be teaching you in the subsequent lectures. So there are different casting processes from injection molding to even hot wax processes and to many other processes. So when we talk about those, like we can synthesis very from very precise to very, mm, I won't use the non-precise term, but very large size of products, like as per our need, like by using casting process, like it has we can say expanded to this much, or it has grown to this much level, like we can even make a very fine surface from this. On the other hand, if you talk about sand casting and all, we get very rough surface. So like over the time it has grown so much, like, so we can't say like it is highly expensive process, but like compared to other processes, it is very cheaper process, casting process. But yes, the cost for like some processes like injection molding, or there are some one or two more processes for like highly polished surface, or have not. I can't use like the term the highly polished, but very fine finished surface. But still, it is comparatively cheaper than other processes. So yeah, so option D is the wrong answer. So yeah. Now if we move to the for phase transformation to take place, like free energy change should be positive, negative, zero, or like free energy does not play any role in the phase transformation. This is a comparatively easy one. So if you have any comments, you may like tell me. So have you read or went through the thermodynamics course, because it is very important topic, and it has application, like major portion of your gate examination will be definitely 4 to 5% will be there, around 10 to 12 marks. And second thing is that if you went to higher studies, then also thermodynamics will be a major portion, because without thermodynamics you won't be able to like survive in your academics, and also in your upcoming interviews also thermodynamics will have a major portion covered in it. So I'll go to a like a small we can say glimpse of del yeah, it is coming from that equation, right? But when we talk about the like basic definition, like firstly you need to go what are the application of the delta g value, and firstly the answer is B, the free energy change should be negative. Okay, and the second thing is like if you go through the application part of this, like what I will suggest you to go, like how the equation delta g is equal to delta h minus tds was derived. And second thing is that you find the applications of this, like when you will write any equation, like suppose you are writing C plus O2 is equal making CO2. Okay, when you will be reading in when you will be reading in certain furnaces, there are like particular zones in it. Like on a particular zone, these reactions are like some reactions are feasible, and on the other hand, some reactions are not feasible. So those are determined by the values of delta G. There are nowadays like there are particular softwares and a lot of database are available where you can find the delta G values for those reactions. Uh, so majorly what the how the feasibility of a reactions is determined. Like suppose you want under a particular pressure and temperature you want to, like suppose I give you an example, like Like if we talk about tin, okay. Uh, so when you will see tin, so majorly what the researchers are doing, like firstly there are two processes like go through. There are like one way is the pyrometallurgy, another way is the hydrometallurgy. So in the pyrometallurgy, as the name suggests, heating what? Yeah, right, right. As the name suggests, pyro means heating. So it is related to the heating, and hydro it is related to the water. So like when you are extracting something from a particular ore, like tin's ore is cassiterite. So like in its ore it is present like around 2 to 3%. So from the 2 to 3% to your 100% pure, to getting 100% pure tin is a big challenge. So like and because there are certain impurities like silica, alumina, and those like in every ore, silica, alumina, and and iron oxide, these three impurities will be more or less will be present. Because and the reason behind this is that when we study the earth crust, like the number one is the oxygen, because that's why majorly elements are present in its oxide form. Second or third comes are the silicon, Si. That's why SiO2 impurity comes. Third or fourth one is the alumina, followed by the iron. Iron is around 5% in the earth crust. So that's why these are the major impurities in each and every of the ores. So when we like I was so if we talk about the hydro processes or as well as the pyro processes, in each of the processes, uh, like how researchers design a process, like firstly they will see like in its ore what like in what association it is present. So suppose there are SiO2, there are certain SiO2 real 2 3, so they will see like by what, if there is any physical process by which we can separate. Or after that, like suppose tin is present as SnO2 in its own, and iron is the major impurity. So will they will see like by magnetic separation can we separate Fe, iron oxide, and then when they get SnO2, they will go like how can we reduce it. So from getting SnO2 to Sn, they will write the Gibbs free energy of that. So firstly they will see at what temperature it is possible, if there are any reductant we can see. So like when we will plot the delta G versus T curve of that, so we will plot SnO2 to Sn reaction, then we will plot the carbon carbon or CO or hydrogen's reaction. So we will check like whether they can be reduced by this, at what temperature it can be reduced. So by that Gibbs free energy comes into the picture. So it should be negative for the feasibility of the reactions, and I will encourage you to go through the derivation and further like how it is calculated, how for each reaction. And in the hydro part, it comes in the terms of EMF series, electromotive series. So there also like cathode and anode cells are made. Then it is seen like whether the equation, whether the reaction will be happening or not. So there also Gibbs free energy comes in picture. So that's why free energy is a very important term, and more or less some like in every gate exam they will be coming in terms of to check whether you have knowledge of that. Like there will be some reactions are given to find out the delta G, then you will check whether it is negative or positive, then you can see like the feasibility of that. So I think I am it's enough for this MCQ, or if you have any doubt. Yeah, yeah, that is called. Yeah, yeah, right. So suppose if you are going to check the feasibility for a particular, suppose tin itself, like suppose some SnO2 it is making tin plus some oxygen, and then if you are using some reductant C plus O2 to make is making CO2, or CO plus O is making CO2. So then you will make a delta G versus T plot of that, or you will check like the slopes of both the equations and at what temperature they are cutting it. If they are not cutting each other, then there won't be any reduction possible for that from particular from that reductant. Then you will go for another reductant or something else. So if suppose questions coming may come from like you are given a plot, certain reactions are given, or in some other plot. So you will, whether they will check whether you understand the basic concept behind it. So if the two plots are cutting each other, not cutting each other, you if you are they may see whether you can extrapolate, interpolate them, and then see whether they at what point they are cutting each other. Then you can find whether what is the optimum temperature for that reaction to be feasible, or from that plot, from the delta G, you just need to read the delta G value for the temperature. But student will get confused in it because they don't know what is the basic concept behind it. So just majorly whenever you are reading for a particular exam or something, understand that term, what it is, how it is derived, and what is the application and significance of that. That's all. You can crack any exam. That's what I suggest. Okay. Okay. So now coming to the fourth question, so the fourth question is surface free energy for for a spherical particle to nucleate is proportional to. One second. Okay. So the fourth one is so I will also take those answers over for the other students who are coming late, because these PPTs will be saved and then they can go through that. So the fourth question is surface free energy for a spherical particle to nucleate is proportional to. So you have any comment on it? Yeah, but how you concluded that? Is there how you came to the conclusion that it is proportional to the square of the particle radius? Is there any some? Yeah. Okay. Okay. So do you know how surface free energy is calculated experimentally? Do you have any idea? So if you see uh, in laboratory and all, what we do for calculating the surface energy of a particular uh, element and all. So contact angle instrument is generally used. So what happens in that, suppose a water droplet is poured onto a particular, yeah, contact angle measurement instrument is used for that. So a particular water droplet or water droplet is poured onto that, it will make a particular angle with it. Then that angle is measured, you can take a photograph of that and that angle is measured, and then with the particular relations and all, you can calculate the surface free energy of that. You can also uh, go through contact angle measurement instruments, how they work and how it is happening, what is the procedure it has. So when the drop, and then the I think the Young's Dupre equations comes in picture for calculating the surface free energy, because each and every, and second thing is firstly you will get the surface free energy, and the second thing you will get with that is the whether the particular surface or the interaction between them is hydrophobic or hydrophilic. So you can determine the hydrophilicity of a particular element, and then also the interaction between them. So one example I will give you again for the tin, because I presently I am working on tin, so that's why these are coming on my mind. So so what happens when uh, so if you talk about tin and copper, suppose, so whenever a tin droplet is poured onto copper, so tin start diffusing into copper, because they form intermetallics onto their surface. So So they form like intermetal, different intermetal like Cu3SN, Cu6SN5. Because this has nothing to do with the course. Just I'm giving you an example because surface free energy came into picture. So whenever we pour the whenever so at each end, and when we talk about the phase diagrams, like suppose you are making a ternary phase diagram for copper, tin, and lead. So I'm just talking about the solder because previously solders used to come from tin and lead. Now lead has been replaced by some silver and other indium based solder also came in picture, but they are also costly. So some copper based solder and some silver based solder came into picture. So when we talk about surface free energy, so suppose as it start diffusing, as the tin start diffusing in it. So what happens, if suppose I need to determine the surface free energy, and if you are and at higher temperature the diffusion is more, so more intermetallics will form. So what I can do, or what we just pour molten tin at 400, 500, 600 on copper surface or some other surface. Just measure the contact angle, and then from that you can see, from that contact angle relationship, what how the wettability of that particular surface is changing. Because more the wettability of it, that will spread more onto the surface, and it will spread more onto the surface, more diffusion will be there. So by that you can see the correlation with that. And yes, the answer, yeah. Yeah, so what happens in soldering process is generally that if your surface tension will be more, that you can calculate by that equation from the Young's-Dupré equation. Just once go to the Young's-Dupré equation after this session ends. So what you will see, like if your surface tension will become more, so that whenever you will be trying to solder two elements, it will start making it won't solder those elements, but instead it will be making some ball type of things because the surface tension is higher. So the tendency of that particular soldering alloy will be to form a ball type of element, soldering ball with tin and lead majorly in it. So that's why some in the soldering some particular waxes or some things are added to enhance its wettability. Because as the wettability will be increased, the surface tension will get reduced. Same from the correlation of the Young's-Dupré equation I'm talking about. So as the wettability will be more, the your solder will spread more on it on the surface. That's what we want in at the time of soldering. Your wettability should be higher. So as your wettability will be higher, it will spread more, and that's why you will get proper soldering it. So just go through the two things here, like two topics here. Like firstly, the surface energy, how the surface energy is calculated by contact angle instrument, and second thing is what the correlation between the Young's-Dupré equation. So that's how your surface free energy concept will be clear, and I think after that you will be able to solve any numerical with it. So yes, the answer is correct. Yeah, yeah, yeah. Because the Young's-Dupré equation is itself like it. So it is a correlation between the surface tension of different surfaces, like your solid and gaseous surface, liquid and gaseous, and solid and liquid surfaces, which is controlled by the angle, between the liquid gaseous and solid. Just you when you will go to that like that relation, you will understand more. So surface tension is the tendency, or it is the force between your like particles in between your particles majorly. So if your surface tension will be more, so like if why it will tend to spread more, because surface tension is due to the cohesive forces of that particular particles, means it is between the inherent particles. When your inner strength is more, why you will go to the some outer or foreign element? So that's why when your like surface tension increases, the solder, which is a major defect in soldering, if you're particularly if you're it is not if it is like what I can say like uh, if was that particular like I just forgot the name. What are the additives added during the soldering? If those additives are not added, uh, it's the solders won't be like wetting your surface. What I mean by wetting, when the forces between your particular soldering alloy and the outer surface on which you are on which you want to do wetting. Suppose I want to uh, like solder two like there I have two metallic chips. One is of copper and one is of like brass. Suppose or two wires. Simply two copper wires I want to add by soldering. So by wettability I mean the forces between your soldering alloy and that copper wire. If it will become more, uh, then it will become more wettability and it will have more wettability and then it will spread more to that particular wire and then it will join those two wires. Or I think I am clear. Or if you have any doubt, yeah. Okay. So and there are more things of that like soldering mechanism. You can also read like how what happens during soldering. So during soldering at the junction point there is intermetallics forms. However, on the after particular depth and all, those intermetallics are not present, and the lead and tin are present in a particular proportion also. So lead tin solder also come in particular ratios like 60-40, 67-33, and 90-10 also. Like 90 is tin, 10 is lead. And now, majorly of these solders are banned because of the toxicity of lead. But still, I haven't seen much change in the electronics. Still, there are solders coming which are comprising of lead. Maybe because of the illegal market, or in India they are just saying that it is banned, but it is not banned. And the second thing is also you can go and study the solidification behavior of lead and tin. Yeah, because the core in this course, as you are reading about the solidification behavior, you can see like the when you will go and see the microstructure of lead and tin, you can see uh, how they solidify, how the lamella structure is made. When you will see the SCM micrograph of lead and tin alloy, you will see lamellas like one particular at one particular region tin will be enriched while on the other particular region lead will be enriched. So that's solidification behavior you can also study, followed by their eutectic behavior at like around 180 or 190. Your 60% tin and 40% lead gets has the eutectic point. So different eutectic points also. So just pick one particular thing, like you pick lead and tin to understand anything. Like you pick lead and tin, and then you just study its solidification behavior. Then all your solidification concept will be different, will be clear. Then read like how the solidification of this lead and tin is different from other alloys. So that's how you will get where are the particular regions are made and where are the other things are being and then from for this lead and tin you can connect this with the soldering, like how the soldering mechanism is being done. For soldering you will need to find how the contact angle and all are measured. So that's how these things will be connected. Then you will see like the soldering mechanism. When you will read, you can see that how the intermetallic formation are there, at what temperature. Then it will get connected to a phase diagram. So in the phase diagram again, the thermodynamics will come into picture. So these how all the things are interlinked, and that's how your concept will get clear and clear, better and better. So I yeah. Okay, so next we will move to the heterogeneous nucleation question. So at question number 5, so it is written that the heterogeneous nucleation may start from. So I think this is already been covered well by Professor Jha in the course itself. It is like very good. He explained very good, like in one particular lecture, how heterogeneous and homogeneous nucleation work and what are the difference between them, and the mechanism also he has explained. So I think it is easy, so I will tell like heterogeneous nucleation may start from, yeah, yeah, mold wall, right? So can you tell me like what is the difference between homogeneous and heterogeneous nucleation? I just want to make the class more interactive. That's why I'm just asking, because it will help. Don't think like if you don't know, I may also don't know certain things, but still that's how we learn and grow. That's the like the thing. Yeah. So like you do you know like what is the difference between? Huh. Okay. So okay. So when you go to the like because it is covered in the Professor Jha's lecture. So when you go there like and just when you will be watching, to see like what is the difference between homogeneous nucleation and the heterogeneous nucleation. So what is the like I'm just saying what are the things you need to consider. Firstly, the difference between those two, homogeneous nucleation and heterogeneous nucleation, any role of impurity in those, their mechanism, and the grain size, like grain distribution, and like how at near the suppose you say mold wall, what will be the particles, and at the center, what will be the distribution. Just focus on those things. Then connect it with the nucleation, like how it starts. Here also, delta G will come into picture. Uh, what particular I just there was one term uh, undercooling something, yeah. So what is the role of undercooling in it? Just focus on those point by point, and then it will be clear. It is not yeah, okay. Yeah, if there is any foreign particle in the melt, then the nucleation will start at the wall as well as the at the foreign particles nearby at the foreign particle. So that's why the solidification behavior of homogeneous what do I say? Solidification of pure and alloying are different. So you can go to the I think it was the lecture number third, yeah, third lecture number by Professor Jha. So to consolidate more your thoughts and ideas. Okay. Yeah, in homogeneous, like suppose if I am talking about lead solution, so in homogeneous only the lead will be present. While if we talk about the heterogeneous and some alloying elements like bismuth is the major. One second, I will just plug in charge it. So that one second. Let's start. Yeah. Okay. So, some impurities are inherent in some elements. So, bismuth is the major impurity which comes in the solders, but it has some very less trace amount of thing. That's why it is not so much difference creates in the solidification behavior. But if copper comes in your solidification behavior of lead and tin, then it will be a big blunder. Firstly, the intermetallics are majorly brittle in nature, so your soldering strength will be will change drastically. And second is the solidification behavior like completely change because lead tin alloy eutectic point comes at around 184, while if your intermetallics are present, then your melting point changes to around 400 degrees centigrade. So your complete chemistry will change. Your soldering will be completely application will be completely destroyed. So that's why the effect of pure and alloying was taught. So go through it and then again go through those questions and then think what are the MCQs. Okay. So let's move to the question number 6, which is the solidification of metal involves. Yeah. Okay. Yeah. Final answer is A only. Yeah. Now, if we go to the question number 6, the solidification of metal involves A. Nucleation followed by growth, B. Growth followed by nucleation. Nucleation and growth occur simultaneously, or D. None of the above. Yeah, right. So, firstly, when you go to that, just see like what are these terms means. What is nucleation? What is seeding? What is the growth means? Like how the grain size, structure, and everything changes. Just go and see. You will easily understand. Yeah. Here, growth means that your size. Yeah. Yeah. Right. Right. That's true. Now, if we move to the seventh question, like the solidification front. So, the solidification front advances in direction of heat transfer. A. B is the advances in direction opposite to that of the heat transfer. C starts from central region of cavity and advances towards wall. Or D, none of the above. So, are you able to imagine this? Like what it is asking? It starts from. Okay. Okay. So suppose like uh, in the subsequent weeks or lectures, you will be studying about the solidification more. So suppose molten metal is poured, like the like you will be studying up more about the riser and all riser pouring basin. Like have you do you know like what is the structure, like how the metal is poured and what and everything else? You have some ideas like what is riser, what is runner? Okay, so once it gets more clear, like suppose I'm pouring a molten metal. Okay, molten metal. So just imagine a simple like horizontal pipe. Okay, and I'm pouring molten metal into it. Okay, and then suppose the question is that the solidification front advances in direction of heat transfer. Okay, and suppose one side is one side temperature is around 50 degree. No, 50 is not possible. Like around 400 degree. And suppose your melt is like lead and tin only. 400 degree on one side, while on the other side it is room temperature. And you are pouring some like or just like you throw water from a bucket, you are throwing molten metal from a bucket into that pipe. So one side temperature because of the molten melt is 400, so it will start flowing due to the fluidity. Your molten metal just once this just it the moment it touches the molten metal surface, firstly there is a bigger temperature gradient, like from 400 it just touched around 25 degree. So there will be a bigger temperature gradient will come into picture, and then there will be viscosity and the fluidity will come into picture, and then the atmospheric resistance and all if we neglect those. uh, so suppose then what will happen? So as the water, as the your melt is flowing from left to right, uh, the solidification front means solidification, its state is changing from liquid to solid. So as your heat is transferred from left to right, because here the heat was higher and there it is lower. As the heat will left to right. So firstly, the solidification will start the moment it touches the pipe. Then only it will travel more. So they are in opposite direction. Have you like imagined it like what I'm trying to say? Uh, okay, so I'm just here. Don't mix with the riser. I'm just saying riser has a different term and different concept involved in it. which is not related to this question. I shouldn't have talked about that in this question. Uh, so their relation will also come, but it is very little stage. So firstly, like suppose your temperature is at a point of your pipe, where like at the moment where it touches the pipe is around 400, and as it move from left to right, the temperature will reduce. Am I right? Are you? Yes. So as I move from left to right, the temperature is reducing. But means heat is transferring. Your heat transfer is taking place from left to right, right? But the solidification will be from right to left. Right to left means uh, yeah, right. Lower to higher temperature, because because the temperature is low, so is like the phase transfer will be easily there. That's why that is in the opposite direction to that of your heat transfer. So I think this question is clear now, right? Okay. So now let's move to the question number 8. So the question is that in the solidification of metals, solidification starts at the mold wall. I think it is repeated. The solidification starts at the center of cast. I think this question has already been covered, no? Is it? So in the solidification of metals, uh, I will take the question for those who might enter late. Okay. Okay, so we were here at question number 8. So in the solidification of metals, okay. So question number 8 is about solidification of metal, and solidification starts at the mold wall. Solidification starts at the center of the casting. At the center of the casting, the melt will be at your higher temperature, because heat transfer is minimum compared to the other surfaces. So B can't be the answer. And if we talk about D, it is not possible. And C, solidification at the center starts before the solidification at the mold wall. It is not correct. So question for it will be the start at the mold wall. Just imagine like how the heat is transferring, where the heat transfer will be more, where the solidification will be there, where just imagine those, and then it will be easily done. So it is A. Okay. Now if we move to the question number 9. Yeah, if you have any doubt. So okay. Which of the following, yeah, cavity means like some foreign particle which is not melt. Are you trying to say that? Yeah, if you are like if you like, these are the things which we like read in the advanced courses, like when we go to the computational fluid dynamics and all, then there these things come into picture, like how the solidification of that particular, due to that particular core, like its diameter, its thermal conductivity, its Cp value and all will come into picture. And then the relevant forces between the particular mold and then their surface will also come into picture. Then the melting point, everything will come into picture. So then you will be writing the Navier-Stokes equation and all. Then you will be solving those. Then you will be doing simulation and all. And after that, you can conclude whether the effect will be more of that due to the particular cavity or due to that particular solidification of metal. Okay, so definitely it will affect, but depends upon so many things, like their materials property, their molten melts property and all. So generally, like previously, like there are some empirical formulas. The CFD is generally like I'm not an expert of CFD, but I just I had been to that course. Uh, so firstly, your basics like computational fluid for fluid dynamics, your basically Navier-Stokes equation and all those concepts will be clear. Once those concepts are clear, you can somehow correlate with those without doing computational things. Like some things comes directly after basics. Your basics are more clear. Computational is just more about like finding the quantitative things, like or like which it will give us more about uh, like what much impact and all it will be there. So it is also a great tool for many of the scientific and all. But morely if you like for the particular core and all, it won't like at your level, like in your exams and all, it won't be asked much. If you ever been to research and all, or for higher study, it will definitely come into picture. Okay. Okay, so now if we move to question number 9, which of the factors affect the center line feeding resistance, CFR? So center line feeding resistance. Okay, so do you know what is this? Okay, so I'll like advise you to go to the lectures because it is covered there, and if you will see like it has like like it is the basically your uh, as the name suggests, center line feeding resistance. Like to feed the central portion, what will be the resistance offered by it? Okay, so to feed the tilt the center of your cavity and all. So it can be like now it can be imagined like by the ratio like total solidification time of your casting, like whatever the total solidification time it took, it will be in denominator, the total solidification, and then in the above it will come the time during which the crystal or whatever your mold is there, uh, like we can say half of your like distance or something. So once you go to that particular CFR formula, like particular this much distance divided by this much total solidification, then you can easily like understand this. So the solidification, so here like the center line feeding resistance, like all the things will be involved in it, like solidification range, superheat, and thermal conductivity of this. So there is a thing called I just forgot the terminology. Something called alpha. I think what we used to say that uh, alpha, which is used to be the ratio of thermal conductivity by your density and Cp, something like that. So that term is highly involved in it. So all these things are related to it because thermal conductivity, like if a material is not even transferring heat from this to this, how easily, how difficult it will be to solidify that. Similarly, if you talk about superheat or solidification range, so if suppose one particular elements solidification range is like only 200 compared to other which is 400, so that definitely will affect this. Similarly, the superheat of that metal. So all the things will be involved, and uh, just read the basics and basic what is CFR. Sometime we okay. Now we will move to the question 10. So I'll answer it about the bow. Now the question number 10 is, which of the statement are correct about the fluidity of the molten metal? Fluidity is affected by the inherent properties of liquid metals such as surface tension, surface oxide films, gas content. Or second one is that fluidity is affected by the pouring related factors such as metal temperature, rate of pouring. Firstly, like, do you know how fluidity is calculated for a particular? Suppose I am talking about some powders. As we talked previously about powder metallurgy. Do you know how fluidity is calculated? So for fluidity there is, yeah, yeah, fluidity is basically calculated using some spiral test. So basically ASTM standards are made like it is a spiral kind of thing. You like at the top of your spiral you put some particular fixed amount, like suppose for 1 gram 5 gram, I don't remember the standard but I know the procedure. So you just pour some fixed amount of powder in it. So as the how easily the fluid will flow through your that particular spiral, which will then there is some relation between the time and the fluidity, which are some there are some empirical formulas. I don't remember those formulas. You can search, but spiral test is generally done for powders, and similarly for molten metals, there is also some test. I am just forgetting its name. So their viscosity and all will come into picture. Then you can do the fluidity test. So fluidity is affected by the inherent properties of liquid metal surface tension, surface oxide film, gas content. Yeah, right. Surface tension, as I previously discussed, surface tension and wettability. Yeah, yeah. You're saying something? Yeah, when you will be reading about the Young's-Dupre equation, so there is a amount of gas. There will be a surface tension between the molten liquid and the gas also. So if that force is more, then your wettability will be more. So that's what you need to see. And then surface oxide film. If your oxides, can you like say why how surface oxide film will affect your fluidity? Yeah, I'm saying like how surface oxide film can affect the fluidity of your molten metal. Like how? So basically, what happens? Your surface oxides, like if I'm talking about tin again. So suppose your at your surface tin oxide is present. So tin oxide will have a higher melting point compared to tin, because oxides are generally more stable than your particular elements. And suppose on your surface tin oxide is present, and at the core majorly your tin is present. So what will happen? So if you as you the melting point of tin is around 254, 250, 254, or something slightly higher. So the core will be in molten state, but your surface won't be in your molten state. So due to your outside is not in the molten state, it won't allow your core to flow outside, because it is in the solid form present. So that's why your firstly, like it will, suppose if you have solder ball, uh, at your surface tin oxide, lead oxide are present, while at the core tin and lead, molten tin and lead are present. Molten tin and lead will melt, they will come in liquid state, while your outside won't come in your liquid state. So it will be remaining in tin oxide and lead oxide. Both are highly stable, tin oxide and lead oxide. I think around 1000 degree, more than 1000 or around 1000 degree temperature they comes in molten state, or else they will come convert to your their respective oxide completely. So the ball will be remaining intact, because your center is still in the molten state. So that's why it will affect your fluidity, because it won't allow your mold to flow. So yeah, second, yeah, it will obstruct the fluid to flow, and as well as some slag part and all will come into picture, which we will read in later stage. So second statement is fluidity is affected by the pouring related factors such as metal temperature and rate of pouring. Yeah, that's true. So the correct answer will be, both statements are correct. It will be C. Okay, so now there are like I have added like five numericals which are very easy to solve. So we will go them one by one, and hopefully we will conclude by 30 more after 30 minutes. So let's move to the question number 12. No, sorry, question number 11. So it is like I will read it for you, then you can try to solve it. Okay. So first one is like equal amounts of liquid metal at the same temperatures are poured into three molds made of steel, copper, and aluminum. The shape of the cavity is a cylinder with 15 mm diameter. The size of the molds are such that the outside temperature of the molds do not increase appreciably beyond the atmospheric temperature during solidification. The sequence of solidification in the mold from the fastest to slowest is, and then the thermal conductivity, specific heat and densities are given. So as I discussed thermal diffusivity, but alpha term sometime before, which is ratio of K by rho Cp. So you can think using that formula. That's one clue for this problem. So take around some time, and then we will discuss this more. Okay, so like which this I just can you say what will be the sequence like this the sequence of solidification in the mold, where it will be fastest and where it will be slowest. Like you need to tell for these steel, copper, and aluminum, like which will be highest from lowest. Can you say? Okay. Okay. Yeah, right. So that is the correct answer. So the sequence will be like this: copper followed by aluminum, and then your steel will come. Okay, so these are determined from this relation. Alpha is K by rho Cp. You can go and see like and then there are like K alpha and density are already been given, so you can calculate your alpha and all. But because all these three things will be affecting those, and then you can like find this copper, aluminum, steel. So it is easy. So we'll move to the next problem. So yeah. So actually, what is here, like when you will calculate the therm, because all these three things will be affecting K also, rho also, and Cp also. So just okay, so just and then we can see like which one is higher, which factor will be affecting more, then we can calculate the alpha value. But all these three things will be affecting our solidification behavior for that particular element: thermal conductivity, density, and Cp. Okay, okay, yeah, right, alpha values, yeah. So if you when you will calculate the alpha for steel by using this formula, so your alpha for steel, alpha for steel, calculate alpha for steel, alpha for copper, and then alpha for your aluminum. Here from here you check which one is the highest and which one is the lowest. So I think copper, for copper it will coming to be the highest. So that's why this sequence will be there. Okay. Okay. Now let's move to the next problem, which is around, which is about blind riser. I'm not. It has nothing to do with your blind riser and all. It is just basics of your mathematics. So that's why I added here, because all these things will come later at your later stage. Okay. So take your time, because it firstly, like at the start, it may take some your time. Okay. So Keynes method, I doubt like whether Keynes method will be used. So what are the answer you are getting? What is the answer? Yeah, right. So, but okay, so you got something relation between h by t. So, what is the thing here is that firstly, if you write the volume term, which is your pi by 4 g square h, this is a general term. From here, you can calculate the h term. Okay, and then you can write your area term. I think you're clear like how I wrote this equation and this, right? Then you can uh, substitute this h term from here, as from equation number 2. here in this equation. So from there, like you will get this relation, 4v by d plus. So like okay, yeah, the pi dh is we're talking about your peripheral areas, and pi by 4 d square is because the bottom part is one part is not in uh, because of that your bottom and top one part is not considered, so only 1 pi by 4 d square is came. Okay, so and is yeah, it is a blind riser now, so one side is not in use. Okay, that's why we will read more about different types of risers in the subsequent lectures. Okay, so that's why 2 pi by 4 d square is not considered, only 1 pi by 4 d square is considered. Now simply you just differentiate it to dA by dt, dA by dt, and equate it to 0, then find the values of relation between your V and capital V, which is volume, and D. Then convert your volume to pi by 4 d square using equation 1, and then find the relation between D and H. So it will be coming around 1 is to 2. So answer will be A. Just solve these equations and then put it. Okay. Okay. So yeah. Can you repeat your question? The riser should solidify at the last. Okay. Yeah. Yeah, it is also acceptable, but it should just at times it will come when you will get confused. It is less or higher. Just remember your shoulder should be like should solidify at the last. Shoulder, sorry. So your riser should be solidifying at the last. So when it will solidify at the last, firstly your molten melt will solidify, then it will solidify. So just imagine, like, suppose T is the solidification time of a mold, and T1 is the solidification time of a melt, and T2 is the solidification time of your riser. So T2 should be greater than T1, greater than or equal. So majorly it should be more than T1, but for the sake of like finding the quantitative value, we write it as greater than or equal to. Okay. Okay. So now let's move to the next problem. It is written that a company is producing a disc-shaped product of 50 thickness and 1 meter diameter using sand casting process. The solidification time of the above casting process is estimated by Chernov's equation, which is T is the solidification time and V is the mold constant, V is your volume and surface area of the casting. And the relation is given as their square and the ratio of the volume and area. Further, it is decided to modify both the thickness and diameter of the disc to 25 mm and 0.5 mm respectively, maintaining the same casting condition. The percentage reduction in the solidification time of the modifying disc as compared to that of the bigger disc. So easily, like you just need to write the, it is written that a disc say product is there. So volume will be pi by 4 d square h, and here both the area from the above and bottom will be considered. Like, so it will be, area will be 2 times pi by 4 d square and added to the pi dh. So that's how you will be writing your Chernov's equation. Then here, from here you can find your relation between your, or convert all everything into one term, like either it is h or it is d. Then similarly you will do for your second thing, like after making the change, like it is decided to modify both the thickness. thickness and diameter of the disc to 25 mm and 0.5 mm. So just change those and then solve it and then find out the ratio, or after determining the ratio, or else directly calculate the percentage change or difference. Okay. Yeah. Yeah, right. So just directly determine the percentage reduction in the solidification time. It's just a mathematical calculation, nothing more. Okay, just you need to focus on the concept. What is the concept behind this? Definitely, it can be asked. So for elliptical shape, your area is pi times your diameter times your height. Pi ds generally. So those areas you can calculate by your by integration and all. Simple integration from this limit to that limit. So those are possible, and they are asked. Trapezoidal shape is also asked. Sometimes elliptical shape and sometimes some haphazard shape will be there. So you need to uh, cut the shape into, or make some triangles or some this and this, make some particular this. So definitely this can be asked. It is not a big deal. Just you need to know how they can be solved. Okay. Okay. So now let's move to next problem. So these are again two simple problems. So 14.1, to manufacture a product by casting molten metal is poured in a cavity of rectangular cross section in sand mold with a side blind riser as shown in the figure. The dimension of the mold cavity are given. The riser is cylindrical in shape with diameter equal to height. It is required to do that the solidification time of the riser should be 25 times greater than that of a mold. To Chernov's rule, the diameter of the riser should be. So this is again the same type of problem. So I just added because these were the things only which were covering the first week and the half of the second week. Yeah. Okay, so try to solve this like, okay. So we have 15 more minutes. After that, we will wrap up. So okay. uh, sorry. Okay, so uh, right, we just need to calculate the solidification time. Uh, so the question was that, one second, dimension of the mold are given, and then it's 25% higher than that of your mold. Okay, so you just need to find your solidification time again by the Chernoff formula, and then you just need to equate one solidification time by 1.25 times of your another solidification time. Okay, and then from there you can find out the diameter. So like it is coming around 36.5 centimeter. Okay, so just try to calculate in your free time. Then okay, so the last question is this. After that, we'll, if you will have any doubt, today's class we will do, or else we'll that. So simply it is again of the same type. The sand casting process has a mold constant of this, and solidification exponent is given. If the solidification time is to be doubled for a given unit volume of material, the corresponding reduction in the cast surface area in percentages. Okay, so like so there is a relation between, you just need to I'll just solve this so as we have seen that T solidification is your relation between this and this, and your area is directly related to 1 by root of your thickness. This you just need to focus. From here you can find out the relation between your E2 and E1 will be coming as root T1 by root T2, and then it will be coming around 1 by 2. From here you can solve this, and then just do -1. So whatever this has value of around 0.707. So just from this, when you do -1, you will be getting A2 minus A1, A2 minus A1 divided by A1. So it will be coming around when you will do -1, around 29, and then multiplying by 100 also for calculating in percentage. So it will be coming around 29%. So this is the answer, and so these were the. I think it is clear. It is not tough. Okay. So then, is there anything you want me to discuss? Yeah. Hello. Actually, your voice is breaking. I think. Actually, your voice broke. Can you please repeat again? Using the freezing ratio, yeah, definitely the questions will be those questions will be covered in the next tutorial, which is next Sunday. So majorly I will be covering majorly numerical portions, and I will be solving more like around 15-20 numericals I will add in the next. And if you got, meanwhile, if you got any doubt, you just mail me, drop a mail. I will cover that also. So okay, so yeah. Uh, Liquid plus solidification shrinkage for aluminum is maximum. Are you saying that? Uh, like I still didn't get your question. Like compared to others like steel and all, are you saying? Okay, okay. So what happens now? Like when you are talking about the shrinkage and all. So as you have already seen the exam trend, like what are these three elements which they are asking. So what you can do, like you can just go through their cooling curves first. Like what are their cooling curves behavior for aluminum, steel, and brass. Okay. Then you see like because each element is different. Because sometimes you might feel why I just need to mug up these things, but that is not the thing. When you will see the cooling behavior of those curves, like every element behaves different. Similarly, like every individual human being is different. So all these elements are that is their behavior, like how they are behaving. So then you will go study their phase diagrams as well as their cooling behaviors. Then you will understand why it is so. Okay. Yep. Okay. So still like bring more questions and like I'll also when like I will know like in what questions you are having doubt. I will prepare accordingly. Okay. So next time it will be more interactive. Hopefully, and more students will join.